So let's look at now this linear case, given that this second derivative trick works in the very general case. Let's see how it plays out in the linear case. In the linear case, I mean y sub I equals a0 phi 0 x sub I plus a1 phi 1 x sub I plus a bunch of phis. And for example, if this was yi equals a0 plus a1x phi 0 phi 0 of x is simply 1, and phi 1 of x is x. This is just, I want to relate it back to a concrete example, because otherwise it's really tough to keep track of what phis and f's and everything is going on. So I'm just tying it back into this established linear relationship. But this is the general linear equation, right? This is the specific straight line linear equation, but really this could be even a quadratic. Any polynomial can still be a linear. Can still be a linear fit as long as it's linear in the coefficients. Okay, so if we ask, if we're taking the so chi squared is going to be the summation over I of yi minus parentheses a0 phi 0 x sub I plus a1 phi 1 x sub I plus dot dot dot. And then this whole thing is squared. And let's see, let's leave in the sigma I squareds too. Yeah, we'll leave them in. So if I want to know the most probable set of coefficients corresponds to the derivative of chi squared space equaling 0. I hate to do this. I've started launching into a derivation without telling you where we're going. Let me go back a step, and then I'll pick this up again, because I really like to know myself. Where we're going is, oh, it's not even shown here. Okay, where we're going is beta equals alpha A. Need a new eraser. And let's see, the uncertainty in sigma squared k is going to be 1 over alpha, no, I'm sorry, alpha, yeah, it'll be 1 over alpha kk. Yeah, I think that's correct. So this is where we're headed. We'll see why that makes sense later on. Or I can just as easily write this as sigma squared k is alpha inverse kk. Maybe that makes you feel better, maybe it makes you worse. Yes?
What is the kk?
Yeah, those are the diagonal elements of alpha. Great question, though. So that's why I have two indices. It's a matrix. So I'm just looking at the diagonal elements. So that's where we're headed. Wow. Okay, there we are. So let's go back and ask, if I know chi-squared space is curved, then the minimum of chi-squared space is going to be the optimum, the most probable values for our coefficients, right? So what is the most probable? Let's just find the minimum. How do you find the minimum? You set the derivative equal to 0, right? The most probable set of coefficients corresponds to del chi squared del a k equaling 0. So let's just take the derivative of chi squared with respect to a sub k. Chi squared is given here. If I take the derivative of that with respect to a sub k, what do I get? A mess. Right? Chain rule. We can do one thing to simplify it. We can recognize, and doing so will give me an opportunity to get a whole new page. We're going to recognize that we can write this as, so we have the derivative of the summation, right? I can recognize that I can rewrite this as a summation of the derivative. Because the derivative of a sum is equal to the sum of derivatives. Okay. On to the next page. Lots of people still writing. You know you're never going to use this. All right. Del chi squared del ak is equal to a summation of I, and then what do I have inside that derivative? I'm going to take the derivative of this thing with respect to a sub k. Well, first thing is a chain rule. I'm going to pull that factor of 2 out and multiply it by everything inside the brackets. And then I'm going to multiply that by the derivative of what's inside the brackets with respect to a sub k. And what is that going to look like? It's going to have a negative sign, and it's going to have phi sub k. Everyone see that? Should I write that out explicitly? Okay. This will be 2 yi minus a0 phi 0 xi minus a1 phi 1 xi minus dot dot dot, not squared, times negative phi sub k of x. Yeah? And then, this whole thing is going to equal 0. So I'm just going to break this sum apart. Now, I know I have this phi sub k I'm going to multiply all the way through. But I'm just going to break it up a little bit. I'm going to write this, I still have this factor of 2 here. I'll pull out. And then I've got a negative. This should be, just to clarify, I'll call this negative 2. And then I've got plus. And this is now going to be a summation. A0 phi 0 x sub I phi k x sub I plus A1 phi 1 x sub I phi k x sub I plus dot dot dot. Brackets. There. I need a bigger screen. Either that or a smaller pen. Okay, that probably wouldn't help. This is the, okay, so if we look over on the left, go back to our expression for linear fitting. Oh, yeah, there's a question first.
That should be divided by sigma I squared.
Yes, it most certainly should. And I'm going to write them as individual terms, the rationale for which will be clear later. Maybe, actually, it might make sense just to pull up the PowerPoint to jog some memories, because it was a long time since I'm sure we talked about linear, the general linear equation. Let's keep that. Don't have it up here. This will be entertaining. Where's the general least squares? Here we go. Yeah, look at this. That looks pretty familiar. Because we just calculated that. That's what beta is. Beta sub k is that. Or beta r in this case. What about alpha? Well, if we go back, now we can go back to the other one. Now we'll get rid of those. Where was I? This term right here, this is one of the elements of alpha. Oh, it switched to red. Oh well, that way you can tell it apart now. This is one of the elements of alpha. This is another element of alpha, and it's multiplied by the corresponding a. So this is really the kth row of alpha multiplied by k, or multiplied by a. So by setting the derivative equal to 0, we essentially have an alternative derivation of our expression that we used for the linear fitting in the first place. And so this ultimately leads to beta. If I do this for every individual k, every individual parameter, then you have beta equals alpha times a, right? So nothing new here. But it's just an alternative way of getting at the solution that we arrived at for the general least squares fit from back in the day. Okay, so that's the first derivative. Now let's take the second derivative of chi-squared with respect to a sub k and ask what happens. Okay, here's the derivative with respect to a sub k. So I'll take the derivative of this again with respect to a sub k, and what do you get? The derivative of the first term with respect to a sub k goes away. Right? The derivative of the second term with respect to a sub k will pull out phi sub k times phi sub k. And everything else in that sum will disappear. What about del squared chi squared del a0 del a1? What's that going to be? By inference. I wrote them this way on purpose. Phi sub k times phi sub k instead of writing it as phi sub k squared. What do you think it's going to be with 0 and 1? Yeah! Yeah, this is going to be a summation over I of phi 0 x sub I times phi 1 x sub I over sigma I squared. Now, why do these look familiar? That's exactly what's in alpha. Yeah. Alpha is just second derivatives of chi-squared space. This is where you're supposed to go, ah, and like have your head just like all the pieces are suddenly fitting together, right? Right? Okay, perhaps. But yes, in fact, the matrix alpha is really populated by second derivatives of chi-squared space. I think there's a factor of 2 I accidentally left out here somewhere, if I'm not mistaken. Yeah, there should be a 2 in there that I forgot to carry through. Now, let's ask ourselves what happens in the absence of covariance in hopes that we can convince ourselves that we arrive at the exact same solution we just derived previously. In the absence of covariance, then the second derivative with respect to a sub I and a sub j is 0 unless I equals j. And so we have only diagonal terms. Does that make sense? Do you want a graphic illustration of what that looks like? Looks like that. So that's choosing a coordinate system based on the principal moments of chi-squared space, which would be equivalent to saying that there is no covariance between the coefficients. So in that limit, then we've got the second derivative of chi-squared space is equal to we know that del squared chi squared del ak squared equals equals 2 times alpha kk. Is that right? So if you have a diagonal matrix, if we want to actually let's rewrite this. I think this will work. So what is alpha inverse? For a diagonal matrix. Well, by definition, the identity must equal alpha inverse times alpha, right? If there's no off-diagonal elements, then alpha inverse is 1 over alpha kk. So if I have, let's see, where am I going with this one? I need to. There's a way to relate that back to the uncertainty. I want to make sure not to screw it up too badly. Oh, okay. Sigma squared k is equal to 1 over alpha inverse? Oh. Okay, yeah, this I think will work out. So if the uncertainty is just 1 over that, then if we now substitute in here, we're going to have that del squared chi squared del ak squared is going to equal 2 over sigma k squared. By substituting alpha kk is 1 over alpha inverse kk, and alpha inverse kk is equal to the variance in sub k, in parameter k. Everyone's still okay with that? Maybe not. Hopefully still all right. Okay. I'll do it explicitly. How about that? Equals 2 times alpha kk. Alpha kk is 1 over alpha inverse. Right? Because of this relationship here. And the uncertainties are given by the diagonal elements of alpha inverse. So the uncertainty in parameter k is, if I solve for this, sigma squared k is equal to 2 over the second derivative of chi-squared space. Which should be satisfying, because that's kind of what we were hoping to get from the previous derivation. So the take-home messages from this, this I should point out, is in the absence of covariance. There's a question, and then I'll talk about take-home messages.
Where did you get that sigma squared k is equal to alpha inverse kk?
Yeah, actually, that's there's two ways of looking at this. That's a great question. One is that if we make this assumption, we get the right relationship. The other is I could have worked backwards. If I assumed that this was correct, I could derive this expression for the uncertainty. So it's a circular argument, which are always the hardest to refute. But the idea is, since we already had a previous definition for the uncertainty in the parameter, if I start here, I could have worked backward to that if I was more clever in my mathematics. But instead I did a proof by induction. If you assume this, then you get the right relationship. Therefore, this must be true.
But how do we know that's right if, pretend we didn't do it in the general case, how do you know that it's right if you make an assumption that's not necessarily valid?
And the assumption is the absence of covariance, correct?
Yeah. Okay,
Yeah.
So it's a...
Yeah, it actually turns out that this is more rigorous, that this relationship is actually more rigorous than the assumption of than assuming the absence of covariance. This relationship holds even in the presence of covariance. This is what's cool about it. So take-home message here. Even in the presence of covariance, the uncertainties in the coefficients are given by the diagonal elements of alpha inverse. Yeah?
Is that assuming we've already diagonalized the matrix?
No. No, this is just, you take beta equals alpha A, right? And A equals alpha inverse times beta. Sigma squared K is going to be alpha inverse KK. Now, what if you have covariance?
That's when we're non-zero.
Well, it'll turn out that that's fine. This still works just fine in the absence of covariance. What we can't do is say that alpha inverse KK is 1 over alpha KK. That goes away. But we can still calculate alpha inverse, and this still holds. Hopefully that made sense. Should I say that again? I'm getting absolutely zero response. All right. Okay, so let's consider the case of covariance. Then alpha 0, 1 is not equal to 0, right? There are terms that are not. There are terms that are off diagonal and non-zero. That's okay. Alpha -1, 0, 0, even in the presence of covariance, will still recover the correct uncertainty in A0. That was the point I was trying to make. And in the limit of no covariance, then the two agree. The second derivative and the alpha inverse agree. They converge to the same result. And so let me just give you, let's go back to that graph where I had those contour plots of chi-squared space. The true uncertainty is really dictated by the curvature along that direction, right? Because that's going to dominate the uncertainty in both A0 and A1. And if we think about just those two, if I just have a two-parameter fit, A0 and A1, that means I have a big off-diagonal term. But when I take alpha inverse, it plays into the diagonal elements in the inverse for both A0 and A1. So the covariance is naturally incorporated into the inversion of that matrix. So we don't have to explicitly consider it. And it yields the proper value for the uncertainty. Yeah?
So you said with no covariance, the second derivative of chi-squared and alpha inverse kk will agree with each other?
Correct.
Okay.
And that's shown here on the left. If I, in the absence of covariance, and the second derivative along that axis does yield the uncertainty in that parameter.
Okay.
But in the presence of covariance, now you can't just, if I take the second derivative along this, it's going to underestimate the uncertainty because I have a trough here and I'm looking sideways across it. I'm going to think that the curvature is less than it really is.
So if you did the second derivative method and tried to work back to alpha inverse, you couldn't do that if it had covariance.
That's correct.
You could only go with the other one.
That's correct.
Could you also just do a rotation of coordinates so that
Yeah, that's interesting. So when I took 621, Fred Lytle made me take it before I could teach the course. He figured I needed to be put through the same pain as everyone else. That's the approach I took because he wrote an exam question where there was big covariance in the second derivative and the alpha inverse yielded different values. And so I diagonalized chi-squared space, looked at the eigenmodes, and got it all to agree really nicely. And then the TA just gave me a big 0 because it was not what was asked. So the answer is yes, you can, but the value of it is questionable because now you've got a frame that is nice and absence of covariance, but it's not directly and intuitively related back to the parameters that you care about. So you definitely can, but its utility is worth the 0 on a 621 exam, apparently. Okay. How much time do we have? Wow, not much. All right. Let me just follow up with one additional point. If the experimental standard deviation is used instead, well, let's see. We already have this one. We already have the one for chi-squared space. S squared is, oh, okay. Then we really take the exact same expression that we had for where sigma squared k was equal to alpha inverse kk, and we just multiply it by the experimental standard deviation of the fit, s squared. And that now yields the experimental standard deviation in alpha or in parameter a sub k.